So, it is basically continuation of the previous class. We are talking a column problem having eccentricity in both the direction. We got the expression of stress and the stress should be equal to 0. From there we got that equation, fine. Now, that equation is basically the equation of the line where stress will be equal to 0. So, beyond that it will be tension, this side it will be compression. Now, if we want the entire cross section will be under compression, there will be no tension inside the section of the column. So, the line should be pass along the corner. So, the corner has a coordinate of x equal to minus b by 2, y equal to minus d by 2, that we have substituted. Now, at this level the value of Rx and Ry we have to substitute. Now, what is Rx? Let us calculate Rx. From there in a similar manner we can get Ry. So, your Rx equal to root over Ixx by E. Now, what is Ixx? So, second moment of area about xx. So, that is B dq divided by 12, B dq divided by 12 into A is B into D. Okay. So, B if you cancel and D is 2. So, it will be d by root 12, or sometimes we can write d by 2 root 3. So, Ry will be your b by 2 root 3 in a similar manner, but here it is Rx square Ry square. So, automatically it will be d square by 12 b square by 12. So, here you can write your minus Ex b, 2 you put below, and Ry will be your b square by 12, and minus it will be Ey d divided by 12, it will be d square by 12 plus 1 is equal to 0. Now, this 2 12 it will be 6, one of the b you can cancel. So, you can write Ex divided by b plus Ey divided by d, that is equal to 1. Right. So, Ex by b plus Ey by d, that is equal to 1. B and D, the actual value we have substituted here. Okay. Now, we want to get the limit of Ex and Ey, right. So, Ex and Ey, again it is giving a curve. Say Ex is a variable, Ey is a variable, it is x by a, y by b is equal to 1, right. So, we can get a curve. No, that is the 6 part we have not taken here. So, y 6. So, it will be b by 6 d by 6. So, it will be Ex divided by b by 6, Ey divided by d by 6 is equal to 1. Now, come to the next page. So, we are ultimately getting more or less this form. This was B and it was D, and just now we wrote Ex by b by 6 plus Ey d by 6 equal to 1. Hello. Now, what is that line? So, what is Ex? Ex we are taking along this. So, here it will be b by 6, right, it is b by 2. So, it will be more or less 1/3, right. and here it will be d by 6 1/3. So we can draw one line. So this value is your d by 6 and this value is b by 6, right, that will be equal to 1. Or we can say Ey is equal to 0. So it is x, it was y. Say Ey is equal to 0, only Ex is there. So Ex equal to b by 6, that already you have obtained. Or if Ex equal to 0, Ey will get d by 6, that also you have determined. If both are there, then if you just join this 2 point, there will be a line, and that is the equation of that line. Okay. So if the load is on that line, your the transition line will pass along the corner, right. So if it is here, the line will be here. If it is here, it will be so if the load is here, the transition line will be here. If it is here, transition line will be there. If we put in between, it will be rotating like this. And if it is here any other point, it will go beyond, right, and if it is here, it will go inside, right. So in a similar manner, if we try to put the load in other coordinate, so we can define a zone, right. So this will be your b by 6, b by 6, it will be d by 6, d by 6. So this part we can define b by 6, b by 6. Here also this part if we define d by 6, d by 6. Now here inside that region, if I put our load on the entire cross section, we will not get tensile stress, it will be entirely a compressive stress, and that area is called core of the column section, right. So what is core? Core is a region, if the load is acting on that, the column section will not be subjected to tensile stress, right. This is the boundary. If the load is at any point on the boundary, means one of the corner point or one of the edge will have a stress is equal to 0, right. Say if it is here, the edge will be 0, if it is here, this edge will be 0, if it is here, this corner will have 0. So something, it will be a limiting case. Now the next part, what you have in your mind, that why you have taken Ex and Ey separately. We could have taken, if there is a load, it is acting at a point having eccentricity in both the direction. So both the direction we can combine. Say the load is acting here, so here to here we can take R, and R can be determined easily. Say this, so this is X, this is Y, this is the point. So we can calculate directly E, right. So this E is root over nothing but Ex square plus Ey square. So here we could shift a moment and normal load plus the stress distribution due to the bending moment, we could take it again. Now here that all the time it cannot be met. The reason is the bending equation whatever we use, or we use My by I for finding out the bending stress when the member is subjected to moment. Now there is one requirement there. the bending will be acting about a plane which should have axis of symmetry. I have tried to draw one figure here. So, this part I have tried to make it symmetric, right. Now, I can draw one figure. Say rectangular section, if I draw, this section is symmetric about this is symmetric about this, but this part is not symmetric about that, right. So, if we apply a moment about this, that formula will not work, or that whatever the idea is there, it will not work. That is circular section, any direction you can apply, but a rectangular section or other type problem, it will not be working. The reason is very simple. It can be nicely explained with a section like this. Say there is a say it is a Z section, right. So, the neutral axis is this. So, this height is equal to this height, absolutely symmetrical, right, dimension wise, but it is not the mirror image of this. So, this part should be on the other side to get a channel. Okay. So, we can say symmetry means if you keep a mirror, if you get the image on the other side, if it is identical, then it is symmetric, right. So, here rather we have put a mirror, again if you put a mirror, so it becomes symmetric, or symmetric is not symmetrical. Now, here what will be happening? Say if we apply a moment, say this is a cross section of a beam and some loading is there, some moment will be there. So, your stress will be My by Y. So, here My and My, it is identical. So, stress at this level will be equal to stress at this level. So, stress at this level will be equal to stress at this level. So, on this block there will be a resultant force and there will be a resultant force, right. Now, they will be equal and opposite. So, if it is a moment like this, it will be compressive, it will be tensile, and they will be equal and opposite. So, total summation of force will be cancelled and they will give a moment, that is fine, and central part is as usual. So, there will be something, this force would be equal to this force, equal and opposite, and it will cancel. Now, this part there is no problem, central part, but this part they will give a moment. Now, this way also there is a distance. Now, they will give a moment in that direction also. Have you followed? So, there are two forces. If they are on the same line, the equal and opposite force they can give moment, but if you keep away, so what will be happening? Due to this height there will be a moment and this side there will be a moment. Now, if you keep a beam, load is there, there will be a reaction. Externally there is no moment. Horizontally we are not putting any load, but if we just follow the equation My by Y, get the stress. From stress, if we try to calculate the moment, we are getting some horizontal moment. Means there is something wrong in calculating the stress with My by I. Means My by I will not work here because it is not a symmetrical section. This is very important because the section should be symmetrical, otherwise your bending, so the resultant of the stress block, they should be on the same line, only there should be a vertical gap. Right. Now, say it will be happening with the angle section also. Say if I draw one angle section, say the centroid is somewhere here. Now about this axis, it is not symmetrical, it is not symmetrical. So if there is one angle, if there is a load, we can't do the analysis directly. Say one of the leg of this angle is say horizontal, another leg is vertical, and load is acting vertically downward. So straightway if we calculate the moment, and from here if we calculate my by, it will not work. Now here what we have to do, we have to take one axis system like this, right. So one of the axis, there should be a line which will divide the section into a symmetrical part. So this part is a mirror image of the other part. Now if we apply a moment, it will generate some bending stress. So this bending stress will be balanced by this bending stress, right. There will be a counter component and they are on the same line. So if there is a bending stress, you have to resolve into two components, right. So one of the axis is your axis of symmetry. So that axis is also not axis, this is not axis of symmetry, but anyway its resultant and its resultant, it will match, because here the stress will have a resultant here, here resultant will be here, automatically it will cancel out. Okay. Now we are talking symmetry, axis of symmetry. Axis of symmetry is something physical phenomena. So from the appearance of the figure of the cross section of the column, we can say this is axis of symmetry. But theoretically, it is one of the principal axis, right. So there is one quantity just now we have uttered, it is principal axis system, right. Any cross section, if we take any arbitrary cross section, if we take this is x axis, this is y axis, we calculate moment of inertia, second moment of inertia Ixx, so it is xx. If it is yy, we calculate Iyy. There is one quantity, it is called Ixy, right. So Ixy is nothing but it is x into y into dA over the section, just like it is integration of it is Ixx is y square d. So if we take one element y square dA, if we integrate we get Ixx, x square dA it is Iyy. So if we take x into y into dA, it is called, sometimes we say product moment of inertia. Now there is one orientation where this Ixy will be equal to 0, and that direction we define as principal direction, right. Now if we have a section and if we get some axis of symmetry, so axis of symmetry will be one of the principal axis, and perpendicular to that it will be the other axis, right. So if we have a section, say this type of section, we are fortunate that there is one axis of symmetry. So without going for calculation Ixx, Iyy, Ixy, we can directly get this is one of the principal axis. So other one will be perpendicular to this, right. But if we have a section like this, this is long, this is short, your centroid is here, there is no axis of symmetry. In that case, you have to calculate Ixx, Iyy, Ixy, and it is not principal direction. So all the quantity you will get, and from there we can calculate Ixy in an arbitrary direction, and that direction if we make that Ixy is 0, so you will get what is the orientation of that direction. So with the second moment of inertia we have to calculate and get the direction. So it may be some direction, and perpendicular to that it will be the principal direction. So any moment when it will be acting, if it is applied in the principal direction, there is no point, we can there is no problem, we can straight away apply the elementary bending theory, that my by I. If it is not along your principal direction, MY by I cannot be taken. So that is the basic reason that if it is in an arbitrary direction with Ex and Ey, we can't combine and take the moment like this, because that moment may not be acting along the principal direction, right. So our bending theory, one of the assumptions we have taken, that the bending moment will give a bending of the member, and the plane of bending, it should be one of the line of symmetry or one of the principal plane of symmetry. So it should be one of the principal axis. So if we take moment in an arbitrary manner, if it is not following the principal axis system, the moment we have to resolve in two mutually perpendicular moment. One will be along one of the principal axis, the other one will be following the other principal axis. After that, My by I you can just apply and combine. Say this type of problem, very trivial, or simply this problem, the load is acting like this. So bending will be in that direction, right. So the bending part, the direction of the bending is this. So that you have to resolve along this and along that. So this bending, it will be like this, and here bending will be like that. So individually you can apply My by I and My by I, then combine both the effect, get the stresses on the cross section. So that's why I was very careful about drawing that diagram, why it is symmetrical and all those. And due to that reason, straight away we can calculate with Ex and Ey. Okay. Now you must have realized the circular cross section is very beneficial in that sense, and if we take a circular cross section, so this is the point which is the location of the centroid. If the load is here, so it is eccentricity in one direction. So if we just follow the approach what we have applied for a rectangular cross section with one directional eccentricity, you can find out the range of this E, so that the limiting point will be here, right. Now in a similar manner, if it is here, because here also it is line of symmetry, so what will be happening, you will get a core having a circular cross section, right. So here if some limit you can find out, say already we know it will be sigma equal to P by A plus your P into E is the moment into it is Y by I. Now you can write, say, P by A, P E, this part if we Y is your D by 2 minus, and if you make this is equal to 0, and I will be how much? It will be pi r to the power 4 divided by 4, or in the form of D, if you write D to the power 4 divided by 32 or 64, I think it is 64. So 2 into 2 4, 4 into 4 16, 16 into 4 64, right. So from here if you try to calculate E, so this P, this part also it is P D squared, right. Yeah, we can write P pi D square divided by 4 minus P E D 64 2 pi D4, right. So from here we can calculate. So pi cancel, pp will cancel. Here it will be dq. So it will be d square, d it will come here. So e will be d into some factor. So factor will be how much? This 64 will be 32. 32 divided by 4, 8. Right. So it will be 8. So d by 8. Right. So it will be E will be d by 8. E is what? It will be d by 8. Now you can put it d by 8. You can put it d by 8, d by 8. So if you follow XY system. Now it is symmetrical. If we take XY in a other manner, it will be also d by 8 all the way. So you will get basically a circular type of cross section, that will be the core, and its diameter will be how much? D by 4. Okay. Now if I take a triangular type of cross section, so there are some very important cases I am taking here. Say it is equilateral triangle. The centroid will be 1/3 from the base, right? Or we can say it is more or less symmetrical. So if we extend this one, this will be the centroid. Now if you put the eccentricity here, some tension will be developed this side, right? So there should be a limit. So E in one direction you can make it, because this is a symmetrical section. So if you put E, there will be a bending, and if you make that limit, something you will get. Now you can think in that manner. You can push the load this side, so there will be a moment, and it will be symmetrical. So there should be some limit, and in a similar manner something. So there should be some triangular type of core here, right? So only this distance you have to find out. If it is equilateral, all the side it will be same amount, right? And you can enclose, that will be the area. So within that, if you apply the load, section will be under compression entirely. So for that type of section, it will be the core. Sometimes we require that information, how will be the geometry of the core and what will be the extent, right? Now I can take one example and at least try to explain how stresses will be generated inside. Say there is a section, say the cross section is it has a square cross section initially. So, this part is A, other side is also A. Now, central part it is reduced to A by 2, other side it is A. Now, here this part and this part, the stress will be P by A. A means area, capital A will be A into A square. Not. Now, here the central part stress will be different. Now, if we are interested for finding out the stress, what will be the stress? Now, if we cut that section, it will be looking something like this. This is your A and this part will be A by 2. So, if we cut and look from top, and the top part it will be square section, it is A, it is also A. So, that was the initial section. Now, it became half, it became A by 2 and A. Not clear? See, here if we cut, so this section is this one, right. So, this is A by 2, the other side it is A, and here it is A, other side it is A. So, here the load is acting here, top part. Now, here it is acting at this point, right. Now, in that case, sigma is straightaway P divided by A into A. Now, here for this cross section, the centroid is shifted to this point and load is here, right. So, here there will be a moment. So, the load is P and moment is P into E. What is E? E equal to A by 4. Right. Now, P into E, so P A by 4 is M. Now, for that cross section, P divided by area here, it will be A square divided by 2, and this P A by 4 is the moment. So, M Y by I, that part will work, right. So, there will be one compressive part, that will be maximum, and minimum part, that will be tensile here, because it is not within the 1/6 range of the core, right. So, it is going to the extreme point, automatically this end will get tension. So, we can get say sigma max, it will be P by A into A by 2 plus P A by 4, that is the moment, and M Y, Y will be your A by 4, and I will be M Y by I. So, I will be the moment about this. Moment about this will be A into right. Now, this part some A you can just make off. So, it will be 4. So, 2 A will go, it will be A square, because it will be A square. So, it will be 2 P by A plus P, it will be there. So, 4, it will be 2, right, and 4, it will be 3. So, 3 into 2, it will be 6 at the top, and A it will be A square, and it will be A square. So, you can write 8 P by A square. Just try to compare. It was P by A square, it is 8 P by A square. So, if the section reduces to half, the maximum stress will be increased 8 times. Right. And definitely you can calculate the uh, other part. So, other part it will be just minus, or here you will get minus. So, there you will get minus 4 P by A square. So, if you want to get stress here, so this part will be intact, only this part will be minus. So, if you take carry over minus, so 6 minus 2, this is a minus part, so major part will be minus. So, it will be 4 P by A square, you will get a half value of that. So, you just try to realize, so section became half and the level of stress it is increased like anything. So, it is not 2 times, it is 8 times. Okay. Now, this is more or less about your short column. Now, next class we will be talking about long column. Long column, the phenomena of failure is entirely different. Let me try to explain a little bit, because some time is there. Here what we are doing for short column. Short column basically, if it is a case where load is acting along the centroid of the cross section, the case is very straightforward, it is P by A, uniform. If it is some eccentricity will produce some bending moment, we have to take some bending stress in addition to the direct stress. So, some of the compressive stress will increase, some part it will be reduced, it may be 0, it may be in the negative side, means tensile stress. So, basically you have to, we are getting here some stress in the form of compressive stress or tensile stress. Now, if we want to do that design, we have to check that the tensile stress or the compressive stress, whatever we are calculating, that should be within our allowable stress. That is our design criteria. Now, in long column, your phenomena will be entirely different. So, long column means here the length part we have not considered. So, we are talking about this is A, other side is A, this is A by 2, this length we are not bothering. It may be 5A, it may be 3A, it may be 2A, any A we can take, right. But this height will be not very long compared to this A, that is the restriction. So, if we study long column, then we will understand there should be some restriction of taking this height, if we try to handle this problem as a short column problem. Now, in long column, the failure mode is entirely different. So, here the failure mode is, we are calculating the stress and try to compare with the allowable stress. Now, if the stress generated within the section, so whatever calculation we have made, we found some stress distribution. Now, if the maximum stress is exceeding the allowable stress, what will be happening? There should be failure of the material, right. So, yielding may occur or shear may occur, basically the material failure will initiate, right. But if we take a long column where the length is quite predominant compared to the cross sectional property, say if we draw here, so it is just P. Say this is quite long compared to the cross sectional diameter. So, it is so long, just I have shown with a line. If there is a load P, what will be happening? It will take care. So, if it is say acting absolutely along the centroidal line. So, P by A, that will be the stress like a spot column, and it will take up to what range? Up to P by A value should be equal to or less than equal to your allowable stress. If you exceed that, then there should be some yielding of the material. So, material failure will initiate. But if this length is quite high compared to this, the limit we are talking about, the P by A, it will reach the allowable stress. So, that is quite far off. Before reaching that load level, we will get the failure of this member in a different form. What is that form? That is called basically the buckling of that member, right. So, there is a term called buckling. So, what is buckling? Buckling is, say here if we apply P, it will take care and it will remain straight, no problem. Now, from side if we give one disturbance, say small load if we apply, it will undergo some bending. Now, if you release that load, it will come back to the original position, right. Say P is equal to say P1, the applied load, and this is Q. Q is some small value. So, if you apply a small Q, there will be a bending, because you are putting some load, automatically it will undergo some bending, and load it will be carried by the member. Now, if you release, it will come back. Now, if it is P1, after that if you go to P2, say it is more than P1, or we can say this P value if you increase gradually, say if it is here, so it will be straight. If you apply a transverse load, there will be a bending. If you release, it will come back again. Now, if you increase the load phi, it will straight, it will remain straight. If you apply Q again, you may get little more bending. If you release, it will come back. So, like that it will be there. Suddenly it will come to a point, if P is equal to that value, if we define this P critical, if we apply Q, there will be a displacement. If you release, it will not come back, it will be there, right. Now, you have to bring back with a force, you have to bring it back with some force. So, it will be there. Now, if you apply more than P critical, still it will remain straight, no problem, because it is below your allowable stress. During that stage, if you apply a force, it will undergo bending. If you release the load, it will not come back, it will not be there, rather it will go on deforming it. So, whole it will try to entirely fail. So, I can give one example here. Right. Now, there is a surface like this, and there is one ball or one object is there, and it has some load, some reactions will be there to take that weight. Now, this is basically P, it is P1 or P2. If we give any disturbance Q, so it will go there, if you release, it will come back. Now, here it became P critical. So, if you give any force, it will come here, if you release that force, it will be there, or if you disturb here to here, it will be there, it will not come back, but it will not go further. But if it is beyond P critical, it will be there, no problem, when there is no lateral force. But if you just touch it, so if you just help it to bring it here, it will not come back, it will not be there, it will go further, right. So, the stage, this is a problem of stability, right. So, it was, this force is balanced by this, it is in equilibrium, this force is balanced by that, it is in equilibrium, it is also in equilibrium, all the cases it is equilibrium, but this is a stable equilibrium. If you give any disturbance, it will come back. This is, if you give any disturbance, it will create problem, unstable, and there is a case it is neutral equilibrium. So if you give any disturbance, the disturbance will not be magnified, but it will be there, but it will not come back. So the column, if we apply a load beyond a limit, if we give any disturbance, so long disturbance is there, deformation will be there. Disturbance is not there, it will come back. So it is a stable range. Now after that there will be a critical stage, it will be this particular condition. So during that load, if we just deflect it and release, so it will be there. It will not go further, it will not come back. And if we apply further load, it will take. So long it is straight, it will take, because this load will be taken by this. But there if you just touch, so there will be a absolute collapse of this member. Now this phenomena is called the buckling of your member. So if I draw the load deflection curve, so this side if it is P and this side if it is delta. So if we apply load, there is a deflection, load deflection curve we plot. Now here if the load is axial, there will be no, so it will be go up to critical range, right. Now critical range, after that it may be this value or this value or this value or any value, it may be in a negative direction also, right. So you can say it will go like this. Now sometimes in some places you will find there is a extension of this line in a dotted form, means it may go there also, but it is a dotted form, means it is in a very unstable region. So if you touch, there will be entire collapse. If it is a critical one, the displacement may be 1 centimeter or minus 1 centimeter or 5 kilometer or minus 5 kilometer this side, right. So that is the critical range or the limiting point, and we have to do that design based on that, and our allowable stress will be occurring somewhere here. So before this your buckling will initiate. Now that is the basic introduction of buckling, which is related to your failure of the long column. So here it is not material failure. What is the failure? It is geometric failure, right. So it is quite long, and due to its typicality of its geometry, that it is a very long cylinder type, so it can't retain its geometry when some load is there. It is not due to the failure of the allowable stresses, not exceeding the stresses beyond the allowable stress. So the material failure will not be there, it is basically geometric failure, but ultimately material failure will be there. So if it is beyond critical load, if you apply, buckling will be there. When there will be excessive deformation, so large strain and material will start yielding. Finally it will be material failure and entire collapse will be generated, but the initial failure or the failure will initiate with the buckling of the member.
The value of P will keep decreasing for the extent of buckling that is taking place.
The load will be
Decreasing.
Load will not decrease. Here it will be constant, after that it may be like this. Now whatever I have drawn, it is very theoretical case, right. Now actual case, the phenomena will be little different. Okay. So here it is straight away, it will go and it will be something like this. Actual load deflection curve if we draw, it will be something like this. Say this is delta, if this is P, say there will be a column here, there is a P. Now we are talking about a ideal case, say cross section will be entirely uniform, load will be absolutely through the centroid, support will be absolutely perfect. Now if there is some eccentricity, load is not acting at that point, it is little bit away. So what will be happening? Some moment will be there. So there is a load and there is a moment, and moment will create some So you go on apply, so from the beginning some bending will be there. So it is not that it is straight, suddenly it will be there. Okay. So there will be a gradual process. So initially it will be happening, if there is some imperfection, the curve will be something like this. Now if you increase the imperfection, it will be like this. If it is like this, if the imperfection is less, it will be like this. If imperfection tending to 0, it will be, so it will be like this. So theoretically, if you try to reduce the imperfection level, it will try to follow this. Though it is a theoretical one, you can't make the imperfection absolutely 0. So depending on the imperfection, your curve will be like this. But theoretically, if it is 0, it will be in that form. Right. Now why you are interested about the theoretical part? Reason is calculation is very easier, this one. Right. So that's why we calculate this, and that will be normally the upper bound. Always actual capacity will be little less. We have the factor of safety to take care of that particular aspect. Otherwise, if we try to calculate this path, we have to go for a nonlinear analysis, because here deflection will be large, and we assume deformation is very small in any analysis. So that assumption is there. So that type of study we can perform if we perform a nonlinear analysis. A nonlinear analysis is quite advanced type of analysis. So if it is straight, we can take this small deformation and perform this analysis. So it may be small or large, it is valid. So in order to make the calculation simpler, we are trying to get a much theoretical case where imperfection is practically 0. Now for perfect case, we put some factor of safety, or we can add something for some level of imperfection, some factor to reduce this, comes down. Okay. So that is the main idea. So actual phenomena is like this, and theoretical part is that, and our idea, if we get that limit, we can assess that will be the level. Okay. After that we can do some adjustment. So that is the main requirement or main parameter we want to find out, what is the critical value where buckling will initiate for a perfect case. So we can keep up to this level today. Next class we will go for calculation of the critical load for different type of problems. So we are talking about theory of column. Last class we have completed the short column part. You must have remember we have divided a column in two groups. One is short column, another was long column. Short column part we have more or less completed. Long column, just what is the mode of failure, how it will behave under the load, what is buckling, all these things we are trying to explain. So it was just the basic structural behavior of a long column. So we will continue with that. Long column. Now if we draw the diagram, what we draw in the last class, say there is a column like this, both ends supported. Now the load deflection curve, you must have remember delta, this was P. Now there was a Now, if it is a perfect system, so if you apply the load, it will directly take that load in the axial manner, there will be no lateral displacement. So, lateral, this delta is lateral displacement, right. So, if I draw the lateral displacement here, say maximum displacement if we try to define as delta. So, normally, so it is a to the power n plus nc1 a to the power n minus 1 b, we write in this form. So, here a to the power n nc1 n minus 1 b nc2 a n minus 2 b square. So, it will go like this. So, it will start with a to the power n, next a n minus 1 b to the power 1. So, next gradually it will change. Now, here if we, so 1 to the power something is always 1, and here first this will not occur, second term it will be nc1 is n is here minus 1 and this part will be there. So, if you take this term, second term it will be d to the power 4 by k to the power 4, after that it will be d to the power 6 k to the power 6. Now, what is d? D is the differential operator. Now, this side there is a constant quantity, right. So, if we multiply, first of all this k square will cancel. Now, it will be basically delta into 1. Second term if you take, so delta, if you take derivative twice, first derivative itself it will be 0, second derivative there is no way of getting any value, and if you take further terms, order of derivative is much higher. So, all the term will contribute 0. So, ultimately we will get y particular is equal to delta. So, we can write the y equal to a cos kx b sin kx plus delta. So, this part was complementary part, this part is the particular integral part. Now, this is the solution of the cantilever beam. Now, next we will put some boundary condition, find out A, B, from there we will try to find out the critical load, right. So, in this class I am closing with that equation. Next class we will try to utilize, try to find A, B, critical load and all those. Okay.